trying to discover how it works and the mechanisms responsible for it, we have to start by talking about atoms. Atoms comprise everything around us, and those atoms are made up of electric charges, both positive and negative electric charges. Typically, these charges are found in equilibrium, so we don't really notice their effects too much, but we can unbalance some of those charges and investigate their effects on one another. Is anybody willing to let me separate some of the charges in and on their body to investigate electric forces? What's your name? Alexis. Let's hear it for Alexis. Right there. I'm going to get my very sophisticated equipment here. I'm going to turn the camera on so we can all see what's going to happen here. I hope not. It's not happened in any of my shows yet, but I'm just kidding. You're going to be fine. Hold on to that so you can see what's going to happen. I didn't tell anybody this at the beginning of the show, but I also am a little bit of a hairstylist. You mind if I restyle your hair?
Yeah!
Do I do good hairstyles? My hairstyles have been described as electrifying and very energetic. Yeah. So here's my very sophisticated equipment here that I'm going to use. Well, you're going to do it today as well. I bet this will be better. Alright, that's fine. So what I'm going to do is I'm going to rub this balloon all over your hair, and I am separating some of your electric charges that are in your hair. I am taking some of those negative electric charges in your hair and putting them on the balloon, which basically leaves your hair a little bit positively charged. And we can see some of the effects here. I'm making it straight, maybe. I don't know. So what do you see happening here, Alexis? Can you feel anything in your hair there? What do you see in your hair? Do you see it standing up? Well, as I bring the balloon closer to her hair, you can see that the balloon and the hair are attracted to one another, right? And you can also see that her hair still stands up when the balloon's away from it, because those positive charges on her hair actually exert a force on one another, so they push each other apart, actually pushes her hair apart. But then the negatively charged balloon, as it gets closer to the positively charged hair, notice there is an attraction between the two. Yeah. And you can see that the opposite charges, the positive and negative, are actually attracted to one another. So Alexis, that is it. You have a lovely hairstyle now, free of charge this time. Let's hear it for Alexis. Now, I would like to separate even more electric charges. Now, is anybody willing to let me do that?
Are we going to reach it? They can't break with their hair. They have balls. One girl. You want me to hold the balloon? Or hold it if you want to go out.
That's you.
What's it?
Kristen, if you will. Stand right on that box.
Ah, it's your body. Her head.
What's
Some
going
of
to
her
happen?
head.
Alright. So, what I have here, Kristen, is a small band of graphene here. It's just like a big one. So, inside here, there are belts that are constantly rotating and actually transferring electric charges up to this aluminum dome. On that aluminum dome, they're deposited and build up until there's enough electric force to push them off of that dome. But since there's a huge amount of insulating air here, so enough force is not built up to force those electric charges off of the dome because it's accumulating on there. Okay? What we're going to do, though, is you're going to have your hand on this dome, put your hand on there. We're going to allow some of those electric charges to build up on the dome, also build up on you. And you are insulated from the ground as well. You're up on this insulated box. And this spider does not allow electric charges to flow through it very easily. So you are isolated from the ground too, so those electric charges are going to build up on you. You have your hair in a ponytail? You mind taking that? hand on there. And we're going to load you up with electric charges. Ready? All right, here we go. Shake your head. Shake your head. More. More. You notice anything? I should give you a mirror as well so you can see what's going on here. This is pretty exciting. Feel a little soft. Let me give you a few more.
Maybe a hair a little bit.
Alright, so all of those negative electric charges are also building up on Kristen and point out the answer for air. Air is light enough to where it's smooth. And that repelling force between those light charges causes your hair to stand up. Pretty cool, huh? Now you can take your hand off the dome now. Hold the mirror with your other hand. I am connected to the ground. I am not on an insulated box like you are. So what I'm going to do now is allow some of those electric charges that build up on you flow to me and down to the ground. You ready for that? So with your other hand, think of this. Give me a fist bump. Ready? Feel that? You guys hear that? See that? Yeah. Little spark? Did you notice her hair?
Yeah.
Do it again. So notice her hair kind of fell each time we did that little fist bump. We made a tiny little bit of lightning and a little bit of thunder as well. Kristen, thank you very much for your helping. Have a seat here, Kristen. All right, so we have separated charges in a couple of different ways here. I did it with a balloon. We started with a small Van de Graaff generator. How do thunderstorms separate electric charge? After all, that is the driving principle of these electric discharges, like lightning. I had a little bit of lightning there between Kristen and I. That little fist bump there. So let's investigate how thunderstorms separate charges. So, let me get my sophisticated props out here once again. So inside of a thunderstorm, these are areas of rising motion in the atmosphere. So that rising motion is carrying tiny little ice and water particles higher and higher into the atmosphere. Eventually they build up enough mass and are heavy enough where they fall back down to the earth. But inside the thundercloud, though, those small rising particles and those large sinking particles actually have collisions with one another. And as they collide, they actually exchange some electric charges. So the small ones become positively charged. The larger ones, as they fall closer and closer towards Earth, go harder. The thunderstorm is a negative charge. And that's how the charges are separated inside of the thunderstorm. And we investigated already the attractive force between the positive and negative regions. So looking at this diagram, where do you think most lightning occurs within a thunderstorm? Do you think it's in a thunderstorm or down to Earth? It's actually 75 to 80% of lightning occurs within the thunderstorm. Some of it, though, does actually make it all the way down to the ground. And I want to show you how that happens. So inside the thunderstorm, you have a discharge between that negative region in the middle of the cloud. There's a tiny little positive region at the bottom. That actually opens up the door for that electric charge to flow all the way down to the Earth, and a path is established to the Earth. First, it looks very forked, very like little fingers moving down, trying to find the path of least resistance down to the Earth. Once that path is established, additional electric charge can go through that channel, and this is all happening in a fraction of a second, so fast that we can't really see this detail with our naked eye. It kind of makes it look like lightning flickers from time to time. But just to give you an idea of how fast this is happening, this is very high speed video. In the bottom right corner of the screen, you see an RV. That RV is moving at 60 miles per hour. So lightning and all these flashes are happening in a fraction of a second. Now, when we see a lightning bolt, what are we seeing? Are we seeing electricity and electric charges? Who says yes? Raise your hand. Who says no? Something else. Raise your hand. Well, let me just put it to you this way. Can you see gravity? No, you can't see gravity. But we can see the effects of gravity. Right? We can't see gravity itself, but we see its effects. Same thing with electricity and electric charges that are flowing through the air. We can't see those charges, but we can see their effects. Those effects are lightning and thunder. Here's a little bit of lightning. So what's happening here is that those electric charges are flowing through the air. They're heating up the air so much that it glows. And they're heating the air up so much that it rapidly expands, actually creates this pressure wave through the atmosphere, which is on an adjacent air molecule, which is on an adjacent air molecule, so it eventually push on your eardrums, and you hear that as thunder. So we can't see electricity or electric charges, but we can see their effects. Now, in a thunderstorm, where's the safest place to go? Inside. Inside is correct. Just remember this little rule. When thunder roars, go indoors. That is the safest place to be in any thunderstorm. But let's say that you're out at a ballpark in the summer, your car is off in the parking lot, there's no real buildings around that you can take cover in. Where do you take cover? The car. Why the car? What protects you in a car? Because the tires are made of rubber. Let's investigate that. You know, I happen to have a tire right here behind me. Here. I can raise that up near the large Van de Graaff generator, see if we can strike it. If we can't strike it, then that tire is doing a pretty good job of protecting us from lightning. However, if it does get struck, I'm going to have to revise our hypothesis a little bit. So let me raise up this tire so everybody can see it. So if you know something about this tire, it's up on these 4 white posts. So as I start the large Van de Graaff generator trying to strike that tire with a lightning bolt, if you see a bolt of lightning between the base of the tire going in between those white posts, then that tire did nothing for us as far as protecting us from lightning. If, however, you don't see that, see basically what you see now, then they did protect us from lightning. So let's see what happens. I'm going to turn on the large Van de Graaff generator here. Again, this will be loud, so protect your ears.